Hello everyone and welcome back to another episode of the Hardware City channel. I know it's been a long time ago since I made the last episode, but I feel like I'm in some kind of continuous loop of apologizing myself for my lacking time resources. So this has got to stop somehow. For this reason, let's dive into the topic now, because I have a very interesting project now to present to you. I started to read this book some weeks ago. This is a book from Mr. Bernd Ullmann about analog computing. Of course, I knew the principles of analog computing from my college time when I studied electronics, but I never dived very much into this subject. Principally, analog computing is that you make some kind of, let's say, hardwired components made out of those tiny little things named operational amplifiers. Operational amplifiers are something that I'm used to since a very long time. You can do signal addition and subtraction with operational amplifiers very easy, but you can also do differentiation and integration. This is done when you add such elements to the operational amplifier circuit. This is a capacitor. A capacitor has a relationship between current and voltage that is specified by a differential equation. And if you doing a differential equation, vice versa, you are getting an integration. So this is the way how you can use operational amplifiers and capacitors and of course resistors to hardwire a differential equation in electronics. And then you can feed some signal in it, you can input a signal, for example a rising voltage or sine wave, and you can do what's coming out of this at the end. So you get a graphical interpretation of the differential equation result. And this is done or shown on the scope screen. Scope screen, you can see both signals, and then even much better, you can apply a special mode with an oscilloscope. I will show you this in a minute. And I don't know the exact term in English. In Germany we call it the XY mode. That means that you have both channels of an oscilloscope. That normally the X channel is where you have the time base running in the oscilloscope, and on the Y channel you can see the signal that you're inputting with a probe. And XY mode, you have both channels free to do whatever you want with it. So there's no time base, you can apply any voltage you want, and thus you can wiggle around and move this little shining point on the scope screen on every position on the screen where you want it to have. So you can do some kind of overlaid images made of two signals that are controlling this little moving spot. Okay, this just as an aside. My second fascination is fractals. I've been dealing around with fractals for a long time, but more in a passive way. I didn't program much. A little, yes, I did program a Feigenbaum fractal in Oberon some years ago, and I tried a little Java. I have a nice book here from Mr. Mario Marcos about fractals, and it's full of nice pictures how fractals can look. This is all done with a program that calculates equations in Java. We also have some pictures that are in color. And I always love this. And I love the similarities those fractals show with structures in nature. For example, a fern, or the curvature of a mountain. And I asked myself, it would be possible to do those fractal calculations, let's say in real time, with analog computing. And I read a little bit in the internet, there are some guys that really do that, so you can also hardwire an equation that's not necessarily a differential equation that uses recursion, so some kind of feedback of values where the output goes back to the input. Can also easily be done with operational amplifiers, and so you get the curvature, or you get a trajectory that's displayed on the scope screen, and you have can directly view the outcome of this fractal. And I was fascinated about this. It's a really cool thing, and I wanted to do this on my own. But the problem is, where do I have those tiny little things here? Just wait. The problem is that I didn't want to dive too deep into those analog computing stuff, because my focus was just on generating fractals. So I considered deliberately if there was an easier solution. You know, engineering is always finding the easy solution for a problem. And I think I had a nice idea. I'm using those tiny little things here. These are voltage controlled oscillators, namely the NE566. Also a circuit that was designed by the famous Hans Kamensein, who also designed the NE555, the most well-known and also still most sold electronic circuit in the world, or at least it was up to some years ago. A voltage control oscillator is a simple thing. It generates a frequency. It outputs a frequency. The frequency is specified by a resistor and again by a capacitor. And those two components are specifying the center frequency of the oscillator on it is running. And additionally, it has an input in one of those pins where you can control the frequency with a voltage. That means normally when you're not applying a special voltage, then the VCO, this is an abbreviation for voltage control oscillator, is running on the center frequency and outputs always the same frequency. But when you apply a voltage to the control input, then you can start to move around the frequency. You can sweep it up and down. For example, if you apply a triangular shaped signal on the sweep input, then the frequency is swept up and down. The frequency is going higher and it's going lower, it's going higher, it's going lower. So it's a direct conversion of voltage into frequency. Good. My idea was to use two of these VCOs, and the output, the frequency output of the first VCO is going into the sweep input of the second VCO. That means this output here, this frequency, is sweeping the frequency of this second VCO. And to make the chaos complete, I wired the whole thing in the way that also the second VCO output is sweeping the frequency of the first VCO. So it's a closed, totally chaotic loop. And I wondered what kind of signal I would get. The second cool thing is, by using two VCOs, you can apply the signal of each VCO to one channel of the scope. So when you run in an XY mode, you have two feeding points for the signal. Let's say the first VCO goes to the X channel and the second VCO goes to the Y channel. And then you have a moving glowing dot on your scope screen that's wiggling randomly up and down, forth and back, left and right, and it's giving you a trajectory. And the question for me was if this would be just total chaos, like noise, without any structure, or if maybe anything structured would come out of this signal. And this is what I'm going to show you in a few minutes. But first I want to explain you the schematic. Läuft das Band? Ja.
Okay, and here you can see the schematic, and as you can see it's pretty simple. Here we have both VCOs, VCO number 1, VCO number 2. Both are configured in the same way. We have a small network of resistors here, 2 resistors, R1 and the potentiometer P1. And we have a capacitor, in this case C1. These 3 components are specifying the center frequency the VCO is running off. It's the same here with the different component designators, but basically it's the same. We also have the same values. The NE566 provides 2 simultaneously working outputs. One is a square wave output, where you get a square wave signal, and the other is a triangular shaped waveform that is emitted. And I chose this waveform, the triangular waveform, for working in the circuit. The reason is that you can't do sweeping operations with a rectangular waveform. This is because a rectangular waveform is specified by jumping forth and back between 2 different extreme levels, and so you don't have all those values in between. This is not suitable for a sweeping operation. For this reason I chose the triangular wave output. This amplifier here is a buffer. It does not amplify the signal, it's just an impedance converter to decouple the output here, which is going to the oscilloscope, one of both channels, and to decouple it from the VCO, just to avoid any feedback reactions. Then we have a second stage here, and the second stage is an amplifier with adjustable output. Here you can amplify the signal that comes from the VCO between 0 and 2 times the amplitude of the output of the VCO. And this signal here is routed directly to the modulation input of the second VCO. And the modulation input, you can see we have small voltage divider. These are for biasing the modulation input in the center, so that you can apply a symmetrical swing around this bias point. Okay, so the output of this VCO is sweeping the second VCO, and the second VCO is absolutely identical wired to the first one, and thus the output of the second VCO is sweeping the input of the first VCO. And that's all. This is a scheme for a perfect chaos. So now let's get our hands dirty. You can see it's already running here, and remember we have 4 parameters we can change. We have 2 times the frequencies of the VCOs, and we have 2 times the amplification in the feedback loop, 1 for each VCO. And I'll show you a little bit what comes out when we are turning those dials. So we start with this, and you can see this is almost perfect noise, but sometimes you can see that some structure is coming through this noise. And this is because this setup here is a little sensitive against the surroundings. This is stray capacitance, I think. And it becomes more clearer if you change a little bit the frequencies. The frequencies of both oscillators are more or less the same now. And you can see we have some lines, and if you turn it, yes, you can see a grid is appearing. Not very stable, but you can see it is a grid. Now we'll try to change the amplifier output a little bit of one of those VCOs. In fact, this what you see here behind the noise, this structure, is a hidden attractor. Because a hidden attractor, by specification, is something like an invisible object that somehow attracts the trajectory of the calculation algorithm to some special paths. That means the trajectory is not to run anywhere at once anymore. It's not perfect chaos, not just perfect chaos. Some parts of the, let's say, of the space here are omitted, are bypassed, and in between where those crisscross grids appear, these are the areas where the trajectory mostly is present. So a hidden attractor is some kind of hidden shape that gets visible because the trajectory encircles it somehow. Okay, we change the frequency a little bit more, and now here it's more stable. Here you can see this is a more simple and more stable hidden attractor because the trajectory path always goes in the same way. The structure of the pattern is not changing. It's a little bit wiggling. You can see it's not very stable. It's not a clear line, but in principle the way the trajectory goes through over the screen is the same. So you can turn every dial here, and you see this is also a very interesting thing. This is a very simple attractor. It looks like a like a mouth or like a slot or slit or a split in the void. Let's see if we can a little bit. Yeah, a little smaller so it's better visible. And if we change the frequency of one of those VCOs a little bit more, then it goes out and in. So this is more or less what you maybe know from the Lissajous figures. This is a way also when you use an oscilloscope in XY mode to check if two frequencies are more or less the same. Similar structures are appearing on the screen. But in this configuration you must consider that we have here two VCOs mutually influencing themselves in some kind of total chaos. And if such thing like this here occurs, then we have a point of stability in the chaos. And it's a very simple and also rigid point of stability, because it's a very simple pattern, a very simple structure, a very simple geometric shape. The trajectory path is moving in. It's just this area here where the trajectory path is moving. It's not in the middle here and it's not outside. Now let's change a little bit from feedback, and you see now it begins to become more unstable and to dissolve. Now it becomes more stable again, and now it's very stable. So this is a point of really rigid stability. Now both VCOs are more or less synchronized. Now I turn it back, and let's change the frequency a little bit more from the other VCO. As now you can see it jumps back into chaos. This is chaos again. Now we turn the frequency up from the second oscillator. You can see that another grid here is appearing. I will make it a little larger. You better can see it. So what I showed you here is just a principle how it works. I spent a very much time to go through all those settings that are possible with such a setup, and I made screenshots of the most important ones and edited them, or made some kind of little video movie out of it, because the best way to identify the interesting parts of the fractal is when you take a movie from the screen and then you look at it really frame by frame, and you can go very deeply into the transition between chaos and stability. And this is where the most interesting things are showing up. And I will show you this now as we came to the end of this
episode in a small video. So have fun and bye, and hope to see you again.
Thank you.